Okay, so good afternoon, ladies and gentlemen. Today I would like to share some results I had with Professor Gianluigi Greco from University of Calabria, and it's about pure strategies in security games. So, of course, before I get to the results, I would like to, I should explain what the names in this title mean in a sense. So, at the start, what is a game? I assume that everyone here has met the notion of a game, the mathematical sense, but just to be clear, so a game in this most basic normal form, we call it is a tuple of three objects where n is a finite set of players of at least two, indexed by I, so solitaire, as you may recall, is not a game in the mathematical sense. Then we have a set of, typically we call it actions, but because of the nature of the paper, we change it to objects as we connected completing action and to picking an object. So for each player, there is a set of possibilities that he has, and we take the Cartesian product of that set, and each vector taken from that set will be a result of a game in a way. Okay, and finally, we need to know what is how much did we gain in a game. So we have this so-called valuating function for which does for each vector from our set O, we get a valuation of how much each of the players gained in that case. Okay, and I think a simple example here is in place. It's relevant to the talk, so bear with me. So yeah, so we have two players, each with one coin. Okay, the coin's sides are distinct. You may not see it from here, but believe me. Okay, we call one heads, the other one tails, and let's call the players lefty and righty. And in a bit of a, let's call it linguistic defiance, the lefty has a goal. He's more righteous. He tends to like order, so his goal is for the both of the coins to have the same side in the end. And the righty is more sinister. He prefers tails, so that sides should be different. Okay, now each of the players takes an action, so he chooses a side in a certain way, in this case random, and on the count of three, they show the sides. We have the same sides, so lefty takes the coin, and then the valuation function would be that +1 for lefty, -1 for righty. Of course, in the case when the sides would be different, we would get a similar but different result. Okay, so this is okay. So this is idea, and this is the idea, and well, I said that we pick the sides randomly in this case, and this is now by no coincidence, because this is basically how we define how the player chooses a strategy, how he decides what he does in a game. Okay, so any assignment of probabilities, if we have a set of actions, one player gives an assignment of probabilities, of course, summing up to 1, so it's a proper assignment of probabilities, to his set of available objects, and that is what we call his strategy. In this case, it would be each player assigned 50-50 to both sides. Okay? If an assignment gives one of the objects probability 1, so it's a deterministic probabilistic function, then we call that strategy a pure strategy. In any other case, we call it a mixed strategy. Okay? Now, and of course, a strategy profile is when we pick up and line up all the strategies that the players use in a given game. Okay, well, this is a strategy, but what makes a strategy good? This is open to debate, a very long debate. So there are different approaches, no consensus by now, but there are some ideas that people recognize as useful, valid, and one of them, those is the Nash equilibrium. So to explain that, we need the concept of the best response. This is a technical definition. The best response is, okay, so the object vector is the vector without his one object, such that we have for each object, any other decision is at least as good. So to put it more simply, consider again this game of matching pennies, and now assume that lefty So when we talk about the best response, we just assume that one of the players has previous knowledge of all the strategies of the other players. Okay, so let's assume that righty has the information that lefty has a pure strategy that consists only of picking heads. Okay, and in that case, the best response would be to pick tails. Also a pure strategy. Yes. Okay, so this is what we usually do. Of course, there is a problem, but because if after that decision lefty finds out that the new strategy for righty is always picking tails, then he will also start picking tails, and so on and so forth. Okay, so in this case, we have a sort of circular loop, but if we can get out of it, if we find a strategy, a set of strategies that we cannot move out by changing the strategy of one player, that is what we call a Nash equilibrium. Okay, so this is basically how we find good strategies, and a little about security games. So this is a game where we add some small additional assumptions about the game. So we divide the set of players into attackers and defenders. Okay, and any object, any action picked by the defenders is called defended. And for it to be a security game, the valuation function has to have the following property. If attacker picks a defended object, yes, then, well, he attacked something that was defended, so his result should be worse than if it was undefended. And a similar thing for the other side. If the defender picks an object and an object that the attacker would pick, then he should have more value than a case when the attacker picked an undefended object. Yes.
Probably more objects.
Yes. Typically, this is a quite large set of objects to choose from. And well, this theory, the theory of security games, has a lot of practical applications. I think it was first used to improve the patrolling schedules on the LAX airport, and is further on used to combat poaching, to program how the federal marshals pick their routes throughout the United States. So this is a very practical, very practical theory. But as a simplest example, if you may notice, the matching pennies is actually a security game, in a way. Yes. If we consider lefty a defender, so someone who wants to coordinate the situation, we get the evaluation function will be exactly picking up what we have here. Now, Professor Greco is studying pure strategies throughout the whole game theory, and he asked, what can we say about pure strategies, using pure strategies in security games, and whether we can find an equilibrium there. So basically, we'll find out. But there were some problems because of the nature of the security game. Because as we saw just in the matching pennies example, yes, when the attacker knows what the defender is going to do, he will switch his strategy. Okay, and also basically in all of the modeling with the security games, we assume that the attacker has the foreknowledge of what the defender will do, as it simulates a situation when the attacker has time to observe the patterns of the defenders and match to that situation. Okay, so in the case of two players, of course, when the situation is symmetric as with matching pennies, once a pure strategy is picked by the defending player, the attacker picks another one, so it's kind of solved in that case. If one of the sides was more valuable, yes, then it's obvious then that the defender should pick that side, leaving the less valuable, from the point of view of pure strategies, leave the less valuable target to the attacker. Okay, so at this point we tried to complicate things a little bit more, so we added more defenders, each with their own agenda, which happens also in the security game theory. It's tested out, and well, we did find out what happens in a typical simultaneous game there, but before that we complicated things a little bit more again, because this is sometimes what you do when you want to find simpler answers. So we gave the defenders a sequence in which they commit to the game. Okay, so now we have a set of n defenders and one attacker. All players have full information of the values of each player, so they know how everyone values the objects in this situation. Only pure strategies are permitted, and the defenders have to commit before to a strategy in known order. Okay, and can we find the strategies that maximize the value for each player in a reasonable time? This is an important assumption here. Yes, because when we have an order of players, for example, I know I'm one of the defenders, and I personally know that a player after me really wants to defend, I know, a rubber duck, because it's very precious to him, and I also really like that rubber duck, but because I know that he will commit later than I can actually pick something else, a teddy bear or anything else. Okay, so we have like this set of possibilities, and the question is, what can we do in that case? So, which model we should pick for this problem? Now the game is in a sequential order. So, first, it's considering the attacker really necessary, and in the sense of pure strategies, no, he will pick after the strategy is defined, so we can just focus on the problem, how to maximize the value of what the defenders have picked. Okay, so we change the problem to an equivalent one. We have a set of players and a set of common objects, so each player uses the same set of possible actions or possible objects. Each player has a value assigned to each object. Okay, and this is common knowledge. And we also know the order in which the players will choose an object. The valuation is a result of the sum of values of objects that have been picked, so if they defend it in the best possible way. So just for the technical purpose, we put the information in a matrix where each row represents a player and each column an object, and the value in the cell represents how much that particular object is worth to that particular defender player. Okay, and how we should decide which object to pick. So again, this is an extension from the game theory. So if we have a sequential game, we can put it in a tree with each node representing the state of the game at this moment, each edge connected to the action that will be performed. So each node, which is not contains information, what moves have been made, the state of the game at the moment, and which player is to move next. Each act from parent to child corresponds to a move made by a player, and the leaf gives us the whole information about the game. Okay, so this isn't a good representation of our game, because of course at each level the number of edges should be one smaller, but this would be a very messy, so this is just a simplification for the purpose of our information. And well, first of all, does a good strategy here exist? The answer to that is yes, and it's from 1910, because in the case of perfect information sequential games, Cermello proved that by a backtracking argument that actually this strategy exists. So problem solved. Not exactly. Chess is also a sequential game where we know we have perfect information, so we know that chess is solvable. It has to have an ending strategy, which doesn't mean that we can say anything about that strategy. We just know about its existence. So here we tried to reason whether we can find out that strategy. Now, and quite obviously, you could write out this whole tree for the game if you have perfect information, but with the expansion of the number of players and objects, this will be completely unfeasible in the sense of time and memory used to find it. Okay, so we try to simplify the thing. Now, if we have sequential games, we need something a little bit stronger than Nash equilibrium to prove that something is good. And so a subgame is just, this is the formal definition, but this is just when we take a subtree. So we picked one of the nodes, and we consider game to move from there forward. Okay, and then subgame perfect equilibrium is a Nash equilibrium that is a Nash equilibrium in the whole game, and every start game. Again, this is to explain all this. I would need a whole lecture, but this is the idea that if something would change, if we would use just a notch equilibrium on this game, sometimes we have suboptimal results in games that weren't played in that result. Okay, so this would be a subgame perfect equilibrium where we defined what moves should be played in each and every possible situation. Okay, so now we decided, but again, finding this whole strategy is time-consuming and memory-consuming. But what we are really interested in is finding that a sequence that goes from top to down and proving that it's the result of using a Nash subgame perfect equilibrium, SPE. Okay, so we defined just that, exactly that. This is a sequence. A result of a game is if we can put a sequence of moves that describes the moving from top to down, and then we say a sequence of actions is reasonable if there exists, without outright stating it, a strategy profile that this sequence will be a result of playing that strategy profile. Okay, so again, we cut from the information that we need. We cut out all of this. We just need to prove that it exists, but the end result is linear with respect to the problem at hand. Okay, and what we did, we did two simple backtracking algorithms to help us prove some theorems about what we are about to do. So this is a very simple algorithm. The idea is that we have the valuation matrix, and we kind of go, first off, we clear all the objects that have been chosen by now. So if we have some information that some objects are picked by other players, there is no need to doubly defend them. That doesn't change the valuation function, so there is no need for that. Okay, then we check how many players are left. For the last row, we pick the most valuable object of that player. We mark it as O of K. We remove the last row, and we repeat the steps until OE is defined. So basically, because this algorithm was the idea is that it's the turn of the ith player. So some moves have been made. The ith player is now to be committing to a decision, and he tries to make a prediction what other players will do. Okay. So this is just basic prediction. He'll pick the best, but sometimes, and this is where the problem in this whole thing lies, there are more than one things to pick, and this randomness is what generates the whole trouble with proving the reasonableness of those sequences. So we had an assisting algorithm which was kind of made for the purpose of proving a lemma that will be shown in a moment, which had this one key difference that it actually he had a prediction of the whole game also added to the information, and it tries to make the output as similar to this prediction as possible. Okay, it's not always possible, but if he has the possibility, he tries to keep it as similar as possible. Okay, and then we did this lemma, which was crucial to the proof, where we show that if we have a prediction and if we throw out one of the objects from the set of given objects and try to do another prediction with the assisting algorithm, we will get at most one difference in the ending result. So we can keep it from becoming totally random. Okay, and well, this is the important part. So first off, our prediction from our algorithm is in fact reasonable. We did prove this is a very technical proof, but basically it's by induction on the number of players. We first prove that for 2 players we can create this strategy. We actually described the process of creating the whole subgame, the whole SPE strategy for the game, but it's a recursive method, so it's very time consuming. But in theory, we can show that it has the properties in the end that we want. So by the number of players, we can go up and find those things up. So we have this theory, we have this predicted result for the first player, and then we gave each and every of the players a chance to use the algorithm, and then the result would be like this. Okay, so totally different because each of the players uses the original algorithm, not the modified algorithm. So on his step, there may be some differences. Okay, and at this point we could say, okay, but what's the problem? We have a Nash equilibrium, so this should be impervious to such shenanigans. But the Nash equilibrium actually saves you from one player. If one player changes something, the result doesn't change, or it's worse for that player. But if several players at once change their strategies, then the Nash equilibrium doesn't save from that. So we have a result, but is it useful? And the answer is, again, yes. In this case, this is the theorem where we just create the sequence from the algorithm for the first player, pick that object, and then for each next player, we subtract the objects picked from the set of objects. We again use a prediction, and we can construct this new sequence like this. And we've proven in a similar fashion to the first theorem that this is also reasonable. Okay, so problem is solved for n players that can pick one object, but actually there is more, because as I said, I will return to this. If the defending players would choose their objects simultaneously, this subgame perfect equilibrium is actually more powerful than the Nash equilibrium. So if you throw out the sequence of play, the sequence that you have from a SPE is also a Nash equilibrium. So this result is a direct consequence of our main result. And moreover, even if we give the defending players multiple objects to defend, not just one object, but multiple, we can still use this algorithm to find the end result, because we can create dummy players that have exactly the same valuations and put them in the proper places in the matrix. So this is done. So where we can go from here, very briefly. As I said, this is solved, but as you noticed, here, we have one result and another result. Both are a result of a subgame perfect equilibrium. Yeah. So the question is that we pose is, okay, maybe whether we can find a little different. A decision problem, if I give you a set of objects, is there a sequence in which I can order the players so that set will be defended? Okay, so this is another, because this is an obvious, if every possible sequence is achievable and so on. So we added an additional player whose goal is actually to achieve a defense of certain set of goals, and then and this was a new decision problem that we found. Okay, and here we did actually prove, well, in a general case, this problem is rather in the class NP. We found a very small class in which it was in P. So for open problems, first off, what would happen? Because in this case where we played, there was no communication between players. So what would happen if we had communication between players? Would that affect the equilibrium? And for the overseas problem, whether there exists a border class in which the problem is in P, and what is the general complexity of this problem. Okay, thank you very much for your attention.
Thank you very much. If you could say something about the example of practical, like real-life application of the algorithm that you propose.
I'm afraid that this is more of a theoretical thing. As I said at the beginning, from the point of view of strategy games, if we know everything about what the defenders do with certainty, there is no decision to be made. We attack the so no, this was discussed, but Professor, as I said, he checked broadcasts for the complexity of the decision problem for pure strategies, so we focused also here. But
okay.
I don't see any,
Okay.
to be honest.
Thank you very much.